At first glance, it seems impossible that something almost weightless and atomically thin could store vast amounts of energy. Supercapacitors rely on surface area. When a voltage is applied, positive and negative charges accumulate on electrode surfaces, separated by a thin electrolyte layer. The more surface area you can pack in, the more charge you can store. Traditional electrodes use porous carbons or other rough materials to maximize this effect, but here lies the mystery. When electrodes shrink to the nanoscale, sometimes only a few atoms thick, they somehow store more energy than expected, reaching capacities far beyond classical surface area predictions. How can something so thin behave like an energy reservoir? One explanation lies in the strange physics of the nanoscale. In ultra-thin layers, the electric double layer, the region where charges from the electrode and electrolyte face each other, can behave differently from bulk models. Quantum confinement and atomic scale roughness can enhance how ions pack at the surface, lowering energy barriers and allowing extraordinary charge densities. In some cases, ions even partially dissolvate, shedding their water shells when squeezed into narrow spaces, which boosts how tightly they can fit. Doesn't it seem paradoxical that confinement, which should restrict, actually increases energy storage? Another possibility is that ultrathin electrodes introduce pseudo-capacitance. Here, instead of simply storing charges electrostatically, the electrode surface undergoes fast, reversible redox reactions that add extra capacity. For atomically thin materials, such as graphene or transition metal dichalcogenides, nearly every atom is exposed to the electrolyte, maximizing their reactivity. In effect, the electrode becomes both a capacitor and a battery, combining the speed of the former with the energy density of the latter. Could it be that nanosheets turn the whole electrode into an active surface with nothing wasted inside? A lesser-known fact is that researchers have observed anomalies where two-dimensional materials like MXenes or graphene show capacitances several times higher than what classical theory allows. This has fueled speculation about exotic interfacial effects, alignment of dipoles in confined water layers, unusual ion correlations, or even quantum mechanical contributions to capacitance. Advanced simulations and in situ microscopy are beginning to probe these mysteries, but no single model yet explains the full effect. Isn't it fascinating that some of our most precise equations fail at scales just a few atoms thick? The paradox is that thickness seems irrelevant at the nanoscale. What matters is how interfaces behave. Ultra-thin electrodes, though almost negligible in bulk, unlock enormous hidden storage because they manipulate ions and electrons in ways that classical models never anticipated. Out of vanishingly small thickness comes immense capacity. The question that remains is whether this effect can be scaled up reliably for real-world devices, or whether it is a delicate laboratory phenomenon. And so we are left with the puzzle: are nano supercapacitors just exploiting overlooked details of classical electrochemistry, or do they hint at new, deeper principles of energy storage waiting to be discovered? Supercapacitors are energy storage devices that rely on electrostatic charge separation rather than chemical reactions. They store energy at the interface between an electrode and an electrolyte, forming an electric double layer. Unlike batteries, they can charge and discharge rapidly while surviving millions of cycles. The energy stored scales with electrode surface area, and inversely with separation distance. Conventional electrodes rely on porous carbon to maximize effective surface. However, nanoscale electrodes challenge classical scaling laws. Their thickness appears too small to account for measured capacities. This discrepancy opens the nano supercapacitor mystery. Activated carbon supercapacitors provide far higher power density than lithium-ion batteries, though with lower energy density. It is like a sponge absorbing more water than expected for its size. Experiments show that ultra-thin electrodes, only a few atomic layers thick, can store enormous amounts of energy. Materials such as graphene, MXenes, and nanomembranes exhibit capacitances far beyond predictions of classical models. Their nearly negligible thickness should limit storage, yet results reveal the opposite. These structures exploit surface-dominated physics that breaks bulk assumptions. Charge storage becomes governed by atomic-scale interactions rather than continuum equations. The anomalous scaling points to new mechanisms at play. The paradox lies in thinness producing abundance. Graphene-based supercapacitors show capacitances several times higher than activated carbons, of much larger thickness. It is like a sheet of paper holding more weight than a thick book. At solid-liquid interfaces, ions arrange into an electric double layer, EDL. In bulk models, this layer is treated as a simple capacitor with nanometer spacing. But at nanoscale electrodes, the entire electrode thickness is comparable to the EDL itself. This amplifies capacitance, as nearly every atom contributes directly to charge storage. Ultrathin geometry eliminates dead volume present in thicker electrodes. As a result, efficiency approaches theoretical limits. The nano-supercapacitor mystery may be explained by this geometry-driven intimacy between ions and electrons. In MXene electrodes, only a few nanometers thick, capacitance scales nearly linearly with exposed surface atoms. It is like every seat in a theater being filled, with no empty rows in the back. Beyond classical double-layer effects, ultrathin electrodes exhibit quantum capacitance. This arises from the finite density of electronic states near the Fermi level. In nanoscale systems, adding charge changes the electronic structure itself, contributing to total capacitance. Materials like graphene show significant quantum capacitance effects due to their unique band structures. This adds an extra storage reservoir beyond ionic accumulation. Thus, quantum mechanics enriches the capacity of ultra-thin electrodes. It demonstrates how nanoscience transcends classical electrostatics. Graphene monolayers show anomalously high capacitance due to quantum electronic contributions. It is like a wallet that expands its size the more money you put inside. Another factor is the confinement of ions in nanoscale pores. When pore sizes match ion diameters, packing efficiency increases dramatically. Confinement alters salvation shells, stripping solvent molecules and allowing ions to sit closer to the electrode surface. This reduces effective separation distance, raising capacitance beyond bulk predictions. At ultrathin scales, nearly all pores participate in storage. This maximizes efficiency and minimizes wasted volume. Confinement thus magnifies the apparent storage density. Carbon nanopores tuned to ion size yield anomalous capacitance, far exceeding predictions. It is like suitcases perfectly fitting into a trunk without wasted space. Some ultrathin electrodes display pseudo-capacitance, where fast surface redox reactions supplement double-layer storage. Unlike batteries, these reactions are confined to the electrode surface and are highly reversible. Transition metal oxides, MXenes, and conducting polymers exemplify such materials. At nanoscale thickness, reaction kinetics accelerate due to short diffusion paths. This creates hybrid behavior, combining capacitive speed with battery-like energy. The extra contribution helps explain mysterious energy densities. Pseudo-capacitance blurs the line between capacitors and batteries. Ruthenium oxide thin films show extraordinary capacitance due to rapid surface redox reactions. It is like a sprinter who also has the endurance of a marathoner. Not all reported anomalies may reflect real physics. Measurement artifacts also complicate interpretation. Contact resistance, electrolyte infiltration, or double counting of surface area can inflate apparent capacitance. AFM impedance spectroscopy and in situ techniques attempt to separate true effects from artifacts. The complexity of nanoscale systems makes precision difficult. Distinguishing genuine phenomena from misinterpretation is essential. Some anomalies may vanish under rigorous testing, yet others remain robust, pointing to real mysteries. Early reports of giant capacitance in graphene were revised after improved surface area normalization. It is like thinking a glass is bottomless until you measure its depth carefully. Despite the paradox, ultrathin electrodes enable transformative technologies. Flexible and transparent energy storage becomes possible with atomic thin films. Integration with microelectronics allows on-chip power sources. Their high power density suits regenerative braking, wearable devices, and pulse power systems. Stability across millions of cycles adds further advantages. Nano supercapacitors combine extreme thinness with extraordinary output. They are both a scientific puzzle and an engineering opportunity. Graphene-based ultrathin capacitors have been demonstrated in bendable displays and microcircuits. It is like a sheet of foil acting as a powerful battery hidden in your sleeve. The paradox is that electrodes almost too thin to exist as bulk materials can store enormous energy. Classical Laplace and electrostatic models predict limited storage, yet nanoscale experiments show the opposite. Surface dominance, quantum effects, ion confinement, and pseudo-capacitance all combine to overturn expectations. The thinner the electrode, the greater the contribution of every atom. What appears fragile and minimal becomes abundant and robust. The nano-supercapacitor mystery reveals new principles of interfacial science. It shows how nanostructures rewrite microscopic laws. A few layers of MXene can outperform millimeter-thick carbon electrodes in energy density. It is like a spider's web, stronger than steel cables, despite being almost invisible.